Okay, so we'll just try and go through. These are two long questions that I picked out. Reminder to spend a few hours studying this weekend. So, okay, it says answer the following questions relating to hydrochloric acid, CH3Cl, and CH3Br. It says hydrochloric acid gas can be prepared by the reaction of concentrated sulfuric acid. There's some typos that should say aqueous, not Ag. Again, these weren't written by AP people. Uh, and sodium chloride, as represented by the following equation. So they give you sulfuric acid plus some salt gives hydrochloric acid plus sodium sulfate. It says a student claims that the reaction is a redox reaction. Is the student correct? Justify your answer. So, what does a redox reaction mean? See if you guys got it. What does redox stand for?
Reduction oxidation.
Yeah, which is the, give me a good definition. Let's see. It's transfer of,
Oh, replacement.
it's the transfer of an electron. Okay, so redox means the gain and loss of an electron. So what we have to do is we have to go through and look at oxidation states of things and make sure that the oxidation states either change, which is in evidence of a redox, or they don't change, which is a different, which is means it's just another type of reaction. So you look at this one and you start, okay, a couple of ways. Usually double replacement reactions are not redox reactions. So this is a double replacement reaction. Um, and you could just cut to the chase there and say double replacement reactions aren't, I think they would give you most of the credit. They might want you to check oxidation states. They might specifically say, what's the oxidation state of something? So here's what you got to remember for the test. So I'll put it up top, oxidation states or oxidation numbers. You should remember that O when it's in a compound is always -2, and H is always +1. And then the other things count for, or they adjust based on the O's and the H's. So O's and H's are always the starting point. And then usually ionic charges, like of metals and things, match, the oxidation numbers match their charge. So for example, when you do this, you calculate oxidation numbers for every type of atom, every element in a compound. So in this, you're going to have to do 3 of them. And if you know that, say, oxygen is a -2, and you know hydrogen is a +1, then you have 4 oxygens, 2 hydrogens, and 1 sulfur. What would that sulfur have to be to make a neutral compound? So you're like, okay, -8 on the 4 oxygens, +2 on the hydrogens. So what sulfur have to be?
+6.
Yep, it has to be a +6. Okay. So in sulfate, SO4 2 minus, you could commit to memory oxygen is a -2 and sulfur is a +6. And so they have to add up to the 1 sulfur and 4 oxygens have to add up to the total charge of that ion. So +6 plus 4 -2s makes -2 overall. So those are called oxidation numbers. Okay, so what are the oxidation numbers on sodium and chlorine? What do you think? You got to guess. What are the oxidation numbers on sodium chloride?
-2 and +1.
Plus
Or
one.
-1 +1.
Yep, +1 and -1, right? So they're just the charges of the ions. So in like salts, you can just go with the ionic charges. In hydrochloric acid, H is a +1. That makes Cl -1, right? And then in sodium sulfate, sodium sulfate's going to look really similar to the other one. It's -2 on the oxygen, +6, and a +2, or sorry, a +1. on the sodium. And so, okay, here's how you determine if something's a redox. You look for each of the specific elements in the compounds and you see, do any of their oxidation numbers change? Like does sulfur's oxidation numbers change anywhere?
No, I think
No.
they all stay constant, right?
Yeah, they all stay the same. So this would be no redox. You could say oxidation numbers don't change. You could say no electrons move. You could probably get away with saying double replacement reactions are not redox. Turns out single replacement reactions and combustions, so single replacement and combustion, those are very commonly redox reactions. There's other types of redox reactions, but mostly from what we know is combustion and single replacement. Okay. So that's an overview. If oxidation numbers, there might be a question about them. If they're confusing to you, just Google how to determine oxidation number and go through a little 10-minute tutorial. Again, the big thing, if you can remember that for the test, you can fudge through much of the rest of it. Okay. Okay, number II. Calculate the mass in grams of sodium chloride needed to react with excess uh, sulfuric acid to produce 3 grams of hydrochloric acid. So this is a stoichiometry question. I probably won't solve it out. We'll just set it up um, and practice that. I just don't want to waste time calculating. So it says calculate the mass in grams of sodium chloride. So you start out with 3 grams HCl. You go from grams HCl to moles HCl. So you'd use molar mass, right? And then to go, what are you going to convert from next? Again, it's asking you to get to grams of sodium chloride. So what do you need to use next?
The molar mass of NaCl.
You will use that at the end. Yep. But we're gonna
No,
go. We're gonna go from
we gotta go from hydrochloric to sulfuric first.
Yep. So we'll do or to sorry to sodium chloride. NaCl. So we're gonna use the mole
Oh
ratio.
yeah.
So the mole ratio here, HCl to NaCl. So I go up there and I look, and it's a 2 to 2 or 1 to 1, right?
Mm-hmm.
And then Keaton, you're right. Then I'm going to use grams NaCl is equivalent to 1 mole of NaCl. So I'll use the molar mass there. Okay, and so we could get grams of NaCl out of that. So there will be, I guarantee, there will be a stoichiometry question. No doubt about it. They would not be able to give you credit for an AP test if they didn't put stoichiometry. So prepare yourself, and you will get the most chem cred if you set it up like that. Okay. So now I picked this one because it has some more equilibrium stuff. HCl can react with methanol vapor, which is CH3OH, to produce CH3I as represented by the following equation. So they give you a new equation and they tell you, so let's just, as soon as you see a K in there, capital K, KP or KC, you're going to think to yourself, does this favor the reactants or the products? So you guys got an answer. Does this one favor reactants or products?
It's products, right?
Very good, because KP is large. It's 4,700, so that's good.
Mm-hmm.
Okay, so just that's a good place to start. You know that this reaction is going to want to go to the right, and it says that you place both of the reactant gases in a 10-liter sealed reaction vessel, and it's allowed to reach equilibrium. The initial partial pressure, so they give you initial partial pressure of methanol is 0.25, and hydrochloric acid is 0.6. Okay, so they give you the starting points. Question I. Does the total pressure in the vessel increase, decrease, or remain the same as equilibrium is approached? Justify your answer in terms of the reaction stoichiometry. So take a look. What's the stoichiometry in that one?
All 1 to 1.
Yep. So now that you've seen that, what would happen as it shifts to the right? Is it going to increase, decrease, or not change the pressure?
It's not going to change.
It won't change.
Correct.
No change.
Okay.
No
Let's say
change.
no change because equal moles of gas on reactant and product side. Okay, so you have 2 moles of gas being consumed and you have 2 moles of gas being created. So it's a net wash. There's no change in pressure. Very good. Okay, considering the value of Kp, calculate the final partial pressure of hydrochloric acid after the system inside the vessel reaches equilibrium. So when it says calculate the final pressure of something, and you've got this capital K, you're going to jump to the ice chart. So I'm going to rewrite it down here below, because this is what you'll have to do during the test. With CH3Cl plus H2O. And they gave us the initial values. They said it was 0.25 mole or 0.25 atmospheres of CH3 and 0.60 atmospheres of hydrochloric acid, and they charged it with none of the products. So then now it just becomes kind of the same process. What's happening to the reactants in terms of their change?
Minus X.
You're losing X. What's happening in terms of the products?
It's gaining
Adding
X.
X.
Yep. So you get 0.25 minus X, 0.6 minus X. You get X and X. So then you set up your fraction, products over reactants equals 4,700. Okay. And now you would solve. Again, I don't think they're going to make you solve this, but I would do it since I have a computer. I would do it on Desmos. So we might as well solve this out so we get an answer. I'm going to cheat and use my, I wonder if I have a TI-89 set up.
I do.
Okay, yeah, we'll have Vincent do it since he's here. Vincent, don't forget parentheses here.
Of course not. I won't forget that.
Vincent and his calculator. It's just like being back in AP Chem.
Mm-hmm. So Vincent will give us our 2 answers. And hey, can you guys remember on Monday and Wednesday next week? Can we let's work on getting together all of our printed materials, like our formula sheet, a periodic table, get like our supplies, so that while we're doing these practice problems, you can like actually physically go through the motions.
Yeah.
Yeah.
Okay.
Mr. Ford.
Yeah.
Do you know until which Wednesday they're gonna let us turn in our books?
Yes, I can look that up at the end of the meeting. There was some emails about that.
Okay.
Yeah.
Because I know they're doing it for like at least next Wednesday, which if our test is that Friday or
Oh yeah.
whatever.
No,
Then
don't turn in your AP Chem book early.
yeah.
We'll take care of that after, even if I have to turn it in.
Really?
All right.
Okay, what's
I got 0.250,
0.250.
0.250,
Okay.
and 0.600.
As the 2 answers?
Yeah.
Wait, and is that rounded?
Yeah.
So it basically is going, do you guys see? It's basically going to completion. Now, which one of these is a bad answer? Like this is probably 0.249. It's probably 0.249 something, right?
Yeah, it's 2499, blah, blah.
Yeah. So, hey, this one, you guys see can't be an answer because if you put in 0.6 there, it comes out negative, right?
Yeah, you can't create matter.
Okay, so we could say X is approximately 0.25, okay, which is going to be the answer. So, and it says calculate the final pressure of HCl. So if you look at HCl and you're like, what's the final equilibrium pressure, which would be this guy, then it's 0.60 minus 0.250. So it's 0.35 atmospheres of HCl. Okay, and that would be the partial pressure of hydrochloric acid. So essentially, this is a reaction that runs one way, and it's going to run one way until you run out of methanol.
Okay.
Okay, so we got that one, and it says part 3 or part I. The student claims that the final partial pressure of methanol CH3OH at equilibrium is very small, but not exactly zero. Do you agree or disagree? And we just determined that we agree. It's small, okay, but it can't go to zero because it's a two-way or equilibrium. You could say equilibrium reaction, right? What's causing this reaction to go forward, to go to the right? What's causing this reaction to go to the right? What has to be present?
Oh, the two reactants.
Yeah. So if this is kind of the crazy thing, if this reaction ever fully depleted the methanol, then it can't go forward anymore, right? And since it's this two-way reaction, you're constantly, if you ever got to zero, then the two products would just push it back to the left. Or mathematically, the way we've set it up, you can't have zero on the bottom. You can't have 0.25 minus 0.25. Otherwise, what's that whole expression equal to? What happens if you get a zero on the bottom?
Oh, then you're dividing by zero.
Yeah, and it's undefined, right? And you get an infinitely big k value, which is not which really you can't do mathematically. So we just at that point we would say the reaction is a one-way reaction. So I think justifying it, you just say it can't go to zero because you get undefined on the bottom, or you say it can't go to zero because it's an equilibrium reaction. Okay, keep going. The table below shows some data for the compounds CH3Cl and CH3Br. So they give you molar mass, they give you dipole moment, boiling point, and the enthalpy of vaporization. So that's how much energy it takes to vaporize 1 mole, so from liquid to a gas, of each of the substances. So, questions. It says, identify the types of intermolecular forces that exist among molecules of CH3Cl. And you guys could probably guess CH3Cl looks something like that. It's just 3 hydrogens and a chlorine off of a central carbon. So what intermolecular forces exist there?
Dipole and London dispersion.
Very good. Very good.
Yeah.
Okay, so we got that one. That should be gimme. It says, in terms of intermolecular forces, explain why the boiling point of bromine, the bromine-based liquid, is greater than that of the chlorine-based. So why is, I'm going to run out of room to type it, but why is this one with bromine, why is it more difficult to boil? Or sorry.
Bromine's a bigger atom, so it has more electrons for London dispersion.
Yep.
This is true.
Yep, there you go. So you just say bigger, so it's stronger dispersion forces, therefore more difficult to boil. Very good. Okay. At 2 milliliter sealed glass vial containing a 1 gram sample of CH3Cl is stored in a freezer at 233 Kelvin. calculate the pressure in the vial at 298 Kelvin, assuming that all the CH3Cl vaporizes. Okay, so first of all, we probably should convert this 1 gram of the 1 gram sample to moles. So is anybody willing? Can you guys? Oh, they give us the molar mass.
Yay!
Okay, so I'm gonna take 1 gram divided by 50.5. Hey, Vincent, can you calculate that for me? What's 1 divided by 50.5?
0.0198.
One more digit. There you go. Okay, that would be moles of CH3Cl. Okay, and then it says, what are you gonna do? Calculate the pressure in the vial at 298, assuming that all of it vaporizes. So this is how many moles we have. Okay. Oh, and I guess, truthfully, that doesn't matter that much. We're gonna do PV equals nRT, and we're gonna first of all collect the things that are constant. R is constant. This is a sealed glass vial where you put a fixed sample in. So what other things are constant or not changing?
Volume is constant.
Volume constant. What else? One other thing.
Temperature. No,
Moles.
no, moles. Sorry.
Moles.
I'm
Yeah.
sorry.
So all we're gonna do is collect those terms. So we're gonna put V down here, and we're gonna put T over here. So P over T equals NR over V.
Or just a constant.
Yeah, or just a constant. So then what I can do is I can say the pressure condition 1 over temperature 1 is equal to pressure condition 2 over temperature 2. Okay? And then I just fill in what I need. So I didn't even really need to calculate the moles because they don't change. Calculate the pressure in the vial at 298. So we want to know P2 at 298 Kelvin. And we know the initial pressure was, let's see, what do we got? Do we not know the pressure? Maybe we're going to have to go calculate the pressure, but we know the original one is stored in a freezer at 233. Why do we not know the first pressure? It's a 2 milliliter sealed glass vial containing a 1 gram sample of liquid is stored in a freezer at 233. Calculate the pressure in the vial at 298, assuming it all vaporizes. Maybe we can't use this condition since it's a liquid. So let me go back. PV, see if we have enough, equals nRT. We probably do have enough. We're solving for P, so that would be nRT over V. And okay, we do have enough. Pressure is 0.0198 moles times R, which is 0.0821 liter atmospheres per mole Kelvin, times temperature. It says it's raised to 298 over the volume, which was 2 milliliters. So, okay, quick conversion. How many liters is 2 milliliters?
0.002.
Yep. So, okay, so there we go. So the fact that, and I didn't catch it before, we weren't changing like a cold gas. This wasn't like it was a gas to start out with. We were given a liquid in a vial and then told that it vaporizes. So if you're changing conditions of a gas, like say you're given a sealed container of gas and you move it to a hotter temperature, then you can use this type of thing. But it has to be a gas condition to a gas condition. Okay, and so I was not paying attention, and so you'd use the full ideal gas law with all the conditions at 298, and you get a pressure of
242.
242, and this would be, wait, 242, that seems huge, but it might be right. Is that
Yeah,
right?
that seems. Well, I mean, it's being divided by 0.002, so I mean.
That's true. It's a very small thing, so that would be 242 atmospheres.
Wow.
Yeah.
Seems like a lot because we're under 1 atmosphere, and I don't know if anything can hold 242 atmospheres.
So let's see. I'm going to look up this question to make sure we're doing it right in just a second. But divided by 0.002. Yep. Okay,
Okay.
so we're gonna say
Really?
242
Wow.
for now, and let's check. Explain. Oh, hey, the next question. I haven't looked at this one. Explain why it would be unsafe to remove the vial from the freezer and leave it on a lab bench.
It might
Because
explode.
it would explode. Okay, and
Yeah.
I'm really curious to see if this. I don't think this was an old AP question, so you guys bear with me. I'm gonna look this up. I'm gonna explain why it would be unsafe to remove the vial.
I need to go.
All right, see ya, Arthur.
So yeah.
Goodbye.
Let's see. Explain why it would be unsafe to remove the vial. See if anybody put one up.
Untitled.
Yeah, but I'm seeing if there's one straight from. See, this wasn't an old AP test question. Otherwise, it would have scoring guidelines. So we'll see what this person from Southampton school said.
That one says AP Chemistry.
Let's see if we can find it. Hey, here it is. Okay, it is in here. So let's check our answers. So we got no, it is not a redox reaction. We got we didn't solve this one out. We set it up correctly. We just didn't solve it. The pressure will remain the same. KP, the final pressure is 0.3, which is what we got. 0.35, which is what we got. This one, I don't think we solved it correct. No, agree. Okay, we agreed. And they said the large value of Kp means that the partial pressure of the limiting reactant at equilibrium will be extremely small, but some CH3OH molecules must exist for the system to be in equilibrium. So we got that one. And then London dispersion forces and dipole-dipole, we got it. The electron cloud and the bromine molecule is larger. We got it. 242 atmospheres, we got it. And at room temperature, the liquid will vaporize. Consequently, the glass vial may not be strong enough to withstand the increase in pressure. Yeah. So 242 is correct. I think it's an unrealistic question, but we did it right. So okay. Do you guys want to stick around? It's been 30 minutes. I don't mind. I have one other one. Do you want to stick around for another?
Sure. I would. Sure.
Okay. I got this one. I think it's from the same test. Okay. So we'll just go through it. I think it might be a little shorter. It says elemental sulfur. So this is the yellow stuff that stinks like eggs. It exists as a molecule with 8 atoms. Okay. And so S8 is represented by the incomplete Lewis diagram above. The diagram of S8 only shows bonding pairs of electrons. How many lone pairs of electrons does each atom in a molecule have? So, if you filled in lone pairs, how many lone pairs would you put on each S?
2.
Correct. Okay. 2. All right. Based on your answer to part A, determine the expected value of the SSS bond angle in the S8 molecule. So, question is, what's that angle?
That would be
1.5.
Yeah.
Very good. It'd be because it's a bent bond angle. Okay.
Yes.
Write the electron configuration for the S atom in the ground state. So sulfur is, I'm gonna have to look this one up. It's element number 16. So we could do it with neon. Neon is 10. So we did this yesterday, and then we'd have 3s. What are we at? 3s2, 3p4. I think this because it was sulfur just like yesterday.
Yeah.
Okay. The complete photoelectron spectrum is for the element chlorine. So now we're moving to chlorine. Is represented below. peak X in the spectrum corresponds to a certain orbital in chlorine atoms. The electrons in this orbital of chlorine have a binding energy of 273. So this would be 273 megajoules per mole. While the electrons in the same orbital of sulfur have a binding energy of 239. So if sulfur had been shown, this would have been shifted this way to 239. Okay, so it says, what does it want us to do? Oh, identify the orbital and explain the difference. So identify what orbital that is and explain the difference between the binding energies in terms of Coulombic forces.
That would be the SP
So out of all these, and it would have been helpful.
S orbital.
It would have been, yeah, it would have been helpful to write out this way: 1s, 2, 2s, 2, 2p, 6, 3s2, 3p, 4. So that's sulfur. So out of all these, okay, down here, which ones are represented by X? The 1s, the 2s, the 2p, the 3s, or the 3p?
Looks like that would be the 1s. Yeah, it'd be the
Correct.
1s.
Very good. So you'd say these are the 1s electrons because they are strongly held, right? So here's, and again, this is how we draw it. So here's the nucleus. If it was sulfur, it would have 16 protons. Well, these guys are held the most tightly because they're the closest to the nucleus, right?
Mm-hmm.
So there you go. So it's 1s, and it says explain the difference. So why would sulfur have uh, a smaller binding energy compared to chlorine? And chlorine is 273. Sulfur is
Uh,
239.
I would say because it's bigger.
Yeah, chlorine has one extra what?
Electron and proton.
Yep, one extra proton. That's why it's stronger.
That makes sense.
Okay. So peak Y corresponds to elements in certain orbitals of chlorine atoms. On the spectrum shown, carefully draw the peak that would correspond to the electrons in the same orbital of sulfur atoms. So again, this is chlorine. So if you guys notice, they don't have it labeled here, but they have 1, 2, 3, 4, 5. So how are you gonna draw? You gotta. There's two characteristics. You're gonna draw a peak. It has to be located and appropriately sized. So where is it?
The next, it's just gonna be and this is the
The one,
oh,
the one
when
that's
it
the one that's drawn is chlorine, and so they want you to just draw in where sulfurs would be.
oh, sulfurs would be one lower, right?
Correct? And would it be to the left or to the right?
Wouldn't it be to the right?
Correct.
Yeah.
Correct. Again, because it has one less proton, right? So you would draw something like that for sulfur.
That makes sense.
And that would be the sulfur 3p peak. Okay. So far so good.
Yep.
Okay. In an experiment, the student studies the kinetics of a reaction represented above and obtains the data shown in the following table. So he did 3 trials. He had some initial sulfur and initial hydroxide, and he measured how fast the reaction went. So he got initial reaction rates. So use the data in the table to do the following. Determine the order of reaction with respect to S8. So you got to look at your 3 trials. Which trials did he try testing the S8? Which trials did he test the S8? Compare like qualitatively, or I guess it wouldn't be quantitatively, try and determine the effect of the S8.
Trial 1 and trial 2.
Very good, because here he varied these while he kept these constant, right? So he kept the hydroxide constant, and he just changed the S8. You guys see, what did he do to the concentration of the SH?
Triple.
Tripled it. When he tripled it, what happened to the speed of the reaction?
It tripled.
It
Yeah,
tripled.
triple. Yeah.
So
About.
if you triple the concentration and it leads to tripling the rate, then is that a first order, zeroth order, or second order process?
That is not.
Oh, that's
Is that?
first order,
Correct.
right?
Correct.
Oh,
So, and the
okay.
way you can think of it, like, remember, the rate is going to always be proportional to this, right? So here you go. What would this exponent have to be, where if you made this 3 times larger, this would also get 3 times larger?
Oh, okay. I see.
X would have to be 1, right?
Uh-huh.
Had this been the case, what happened if X is 2? What would have happened to the rate if you tripled the concentration? What would
Oh,
happen?
then it would 9
It would
times.
be 9 times faster, and that would be second order. And then
Yeah.
what would happen if it was zeroth order and you tripled the concentration? What would happen to the rate?
Nothing would happen to the rate.
Correct. It would stay the same. So because we know it tripled, we know it's first order. Okay.
Okay.
And you could just say it's first order because tripling the concentration tripled the rate, and that's justification.
Cool.
Determine the value of hydroxide that was used in trial 3, considering that the reaction is also first order in respect to hydroxide. So here you're going to look at trials 2 and 3 because he kept these constant. And the question, what happened to the rate?
Oh wait.
It doubled. So then what would be a good approximation for the hydroxide, assuming it's first order?
Probably doubled.
Yep.
Doubled, so 0.02.
Yep.
Oh.
That's it. So yep, you just look at it and you gotta compare. So
Okay.
okay, the next day the student conducts trial 4 using the same concentrations as SH and hydroxide as in trial 1, but the reaction occurs at a much slower rate. The student observed that the temperature in the lab was lower than it was the day before. Provide 2 explanations that help account for the fact that the reaction rate is slower in trial 4. So one, we know that its temperature was slower. So I don't know, provide 2 explanations using particle level reasoning. So
I think I know what they mean.
yeah, okay, what do they mean?
They mean that you have to use the what happens to particles in relation to something else. So,
Yeah.
like, the first response would obviously be that the temperature went down, so the amount of impacts that the molecules are hitting at decreases. The second one, I don't know.
Which is lower kinetic energy, you could say.
Yeah.
Okay, so you could say, yep, lower kinetic energy. So so particles don't have enough energy to overcome
Activation energy.
activation energy.
Okay.
And let's see what they said on their test. But I agree. Those two would be pretty. That seems like good answers to me. So let's look up what they said. And I think it was the same test. I thought I saw it on here.
Yeah, no. All these questions are from that one page I saw.
Oh yeah, here you go. Okay. So we got the peak. We got the peak in the right spot. We got first order. We got 0.020. And here you go. It says the temperature was lower on the second day, so the average kinetic energy was lower. Therefore, fewer collisions between particles with sufficient energy to react. So there's the activation energy one. And since the temperature was lower, the kinetic energy was lower, and the average speed of the particles were lower. At the lower speeds, the reactant particles collided less frequently. So we got the same 2 answers. Very good.
Nice.
Yeah, very good. If you guys did that, if you were able to go through those questions, you would get fives for sure with how you did it, and you were on today. So yeah, very good.
Nice.
Hey Vincent, I'm gonna try and run to the school today. I have a digital camera that I use for track. So will you be around your house today if I was to drop it on the porch?
Yeah, I would.
Okay, I will try and email you when I have a better ETA. It will hopefully be sometime this afternoon. If not this afternoon, then this weekend.
Okay.
So, and I'll try and it has an SD card, and I'll try and get you an SD card reader. Do you have any way? It's just a standard size SD card. Do you have any way to read that on your computer right now?
Yeah, I've got an SD card slot right here.
Okay, perfect. So I'll just get the camera, a charger, and a SD card, and then you can test it out.
As long as it's not mini SD card or something.
No, it's a standard SD. Okay, so I'll do that. Keaton, do you have any questions? Oh, I was gonna look up your book,
Yeah.
right? Let me look it up on my other computer. Gmail. It's looking right now. Oh, and I'm gonna stop recording.